All right, well, welcome everyone to Chapter 4. This will be the first video I'm doing in Chapter 4, and so because it's the first one, I wanted to talk a little bit about the basics and the fundamentals of projectile motion and what it looks like, right? What the trajectory of a particle looks like as it's, well, projected through the air, right? In case you've never tried to watch or study the motion of an object after you've thrown it, most of us haven't, you may be surprised at what it actually looks like. Okay, so to start, let me draw an axis here. Right, there's kind of up and horizontal. Okay, so my question to you is, to start, once you throw a ball, for example, a baseball, into the air at any angle, let's say you just throw it up, right? What forces are at play? We haven't talked about forces, that's really next chapter in chapter 5. But intuitively, you may already know what force is on the object during its flight in the air, right? That force is the gravitational force. And it turns out that that is the only force. Well, I shouldn't say that. Technically, there's air resistance, but for this entire class, we're going to ignore air resistance because it's much too complicated. So for our purposes, there's only one force on it, okay? The gravitational force. And that acts such that it always wants to attract this object back down towards the ground, okay? And so when you throw an object at whatever angle, say 60 degrees to the horizontal. So let's say you throw it like that, right? Some V naught at 60, okay? What's its trajectory through the air going to look like? Will it look like a perfect semicircle? Like that? Right? Or will it look more like a... That's not what I was going for. Let's do this. Will it look more like a... That's slightly worse. Let's try this again. Something like that. Will it look more parabolic? Right? Which one's true? Well, if the gravitational force is the only force acting on it, you'll see next chapter that means that the object will continuously slow down or speed up. Okay? If it's traveling upwards, right, if it's traveling initially upwards, the gravitational force, I'll write it, is actually down. So we'll write its acceleration is actually down, right? And you'll see in this chapter that that's actually equal to a magnitude of 9.81. In fact, we've talked about this in chapter 2, but it's really applicable here in chapter 4 as well. It has a magnitude of 9.81, and we know it as little g. Okay, that is directed down. And so that's effectively pulling down this object as it moves up in the air, slowing it down to a stop in the vertical direction. Okay, so if you look closely, right, this perfect semicircle right there, near perfect in this case, its motion in the y direction decreases uniformly, right, or much closer to uniform than it does for a parabola. Okay, so it turns out that because there's only one force on it, and the motion caused by that force decelerates this object, its motion is parabolic. And so it turns out that its motion is not circular like that, it's parabolic. And actually, let me extend this out a little bit. And I'll actually go down, and you'll see why later. Okay, so let's take a look at various points in this trajectory. Okay, so first off, the particle object starts out with some initial velocity. I'll draw that in red. v naught, right? And let's take a look at the components to that speed. Initially, in the y direction, I better keep it at the same magnitude. There you go. Initially, that component is, well, straight up, and it's of whatever magnitude, right? We'll see how that magnitude compares later on. In the x direction, do I have another color? Let's do, how's light green? Terrible. Let's do dark green. In the x direction, it has, well, that magnitude, okay? Now, about halfway to 2/3 of the way up, right, what does the speed at that point, the instantaneous speed at that point look like? Well, it's got to be tangent to the trajectory, right? It's going to look something like that, such that the vertical component has roughly that magnitude now. The x component has that magnitude, right? Notice the difference between the two. It started out vertically having a magnitude of say, that long, right? And then as it traveled up, the magnitude has decreased, right? It decreases speed, it changes speed because there's a force on it, the gravitational force. Thus, there's a net acceleration downwards. And so this delta v here, this final minus initial, is negative. That means that there's a acceleration downwards, or a negative acceleration. The x components in green here, v naught x to vx, they should be the same magnitude. And I've tried to draw them roughly the same magnitude here. Why would they be the same magnitude? Because there's no forces in the x direction, right? There are no horizontal forces. Thus, the magnitude of the speed in the x direction for all points along this path, the x component is the same. The speed does not change. Okay? So now let's take a look at the apex, right? At the very top. Well, in red, its speed, its tangential speed, will be something like that. Actually, it'll be slightly less, right? Vertically, its y component, well, it's not moving up or down. Y component, 0. So up top, Vy equals 0. In the x direction, well, that turns out that that's now the same magnitude as what I've drawn in red. So again, the horizontal component has stayed constant, and I've tried to draw the magnitude of the tangential speed in red to decrease a little bit, right? Such that it has its minimum speed at the very top, right? All right, if we keep going down, let's go straight over to here at this point. In red, something like that, right? It'll basically be the opposite to what we have on the left. So vertically, now it's going down with what should be the same magnitude of Vy as over here, right? Why is it the same magnitude? Well, if we think about it, it's had the same amount of time to travel from launch, right? From launch up to this height. It's the same height off the ground. It will have the same time to reach from this height back down to its launch height, okay? it will also have had the same time to go from this height up to the apex height, and then from the apex height back down to this height, right? Because these are the same height. And because that has the same difference in heights right there, and the force of gravity is not changing, the magnitude of the velocity at the same height in the trajectory is the same. Okay? So in green, as before, Vx is constant. I haven't written Vy. Again, this Vy right here is the same magnitude as this Vy over there because it's at the same height. Okay? More specifically, it's had the same amount of time to go up to the apex as from the apex back down. Thus, the force of gravity has had the same amount of time to act on it, to decelerate it to a stop and then accelerate it from a stop. Okay? If we keep going back down to the initial launch height, something like this, right? And if we take a look in the vertical direction again, it should be just like before, the same magnitude as the start, right? So this Vy, that component, should be the same magnitude as what our vertical component was initially. Again, same height to go up, and then from the apex back down. The x direction has not changed. That is still, no longer V naught. That is still Vx. Notice this entire time, these components in blue and green have added together, right? They're both perpendicular. They've added up vectorially to be the vector in red at all points. Okay. So now, question for you. If we let this object fall down lower, right, past its starting height, let's say it was shot up, reached the apex, has come back down, and now has passed its starting height. Let's say it's down here. What will the speed be compared to what it started at? Right? It turns out that it will be faster. Right? It'll be even faster than what it started because it will have had more time to go from a stop all the way down here. It will have had more time to be accelerated via gravity than the time it had to be decelerated from launch up to the apex. Right? So the difference in heights means that the force has had a different amount of time to change its speed. Okay? And because of that, the vertical component, I know it's not really matching, but the vertical component should be greater than what the initial was. However, in the x direction, once again, it's still the same. Has not changed the magnitude. Okay? So this is the crux of parabolic motion, right? For a projectile, any object sent at any angle through the air, subject to only the gravitational force, right? Its path, its trajectory, in other words, follows a parabola, right? And this applies for angles of 0, right? In other words, it can be launched straight. That's kind of a half parabola, if you will. It'll just go like that, right? It applies to any angle in between. It even applies to 90. It can go straight up and come back down, right? That's a infinitely squished parabola, right? But applies for any angle. Projectile motion in 2 dimensions sweeps out a parabolic trajectory. All right, thanks for watching.